Hello everyone, we will discuss today linear momentum and collisions. As we discussed previously, the mass is correlated with velocity in a quantity called kinetic energy. So kinetic energy is defined as half mv square, and the kinetic energy here is related with v square, and we mentioned that kinetic energy is a scalar quantity. Today we will discuss a new physical quantity. It's called linear momentum. It's equal to mv, and linear momentum is a vector quantity it's measured in kilogram meter per second. Unlike kinetic energy, linear momentum is proportional with v. Since linear momentum is a vector quantity, then we should have three components for the linear momentum. It's px, mvx, py, it has to be vectors, mvy, and pz equal to mvz. In this model, we can see here a car with mass 1 kilogram here and the velocity equal to 0. The linear momentum for this car is equal to 0. Once we increase the velocity to 1, so the linear momentum becomes 1 kilogram meter per second. You can see here. Now, increasing the velocity to 2, the linear momentum becomes 2 kilogram meter per second. Changing the mass into 2, so the linear momentum will be mass times velocity. 2 times 2, it's equal to 4 kilogram per second. Now, decreasing the velocity to 1 here, and the mass is equal to 3, the linear momentum equal to 3 kilogram meter per second. As we can see here, linear momentum is directly related with the mass and velocity. Now, changing the velocity will be directly correlated with changing the linear momentum, and modifying the mass will also modify the linear momentum. Now let's back to Newton's second law. Sum of all forces equal to ma, or F net equal to ma, and we all know that a is the first derivative of v with respect to time, and in this case here F net equal to d. Since mass is time independent, we can include it inside the derivative here, mv by dt, and F net equal to dp by dt, or in other words, F net equal to delta p over delta t. Or in other words, F net is equal to the change in linear momentum with respect to time. Let's see this model. Now in this model here, if we apply driving force equal to 5 newtons, as we can see here in this model, it's just here, this is the momentum with respect to time. Now, as we can see here, F net equal to delta p over delta t. In this case, the slope of this line is equal to f net. Now let's check here. If this is 4 and this is 0.8, if we take this one here, 0.4, 2. Now in this case here, f net equal to 4 minus 2 divided by 0.8 minus 0.4, which equal to 5 newtons. This one here is the same as what we started with. Now let's have this example. An open cart rolls along a frictionless track while it's raining. As it rolls, what happens to the speed of the cart as the rain collects in it, assuming that the rain falls vertically into the box? So we have here a cart like this one here, and the rain falls vertically into this cart. So what happened to the speed of the cart and the momentum? Since the rain falls vertically, the momentum here, the momentum is conserved, which means the rain adds no momentum to the cart because it falls vertically. But the mass of the cart will increase and the velocity of the cart will decrease. So the mass will increase and the velocity will decrease. After all, momentum is conserved. Let's have another example. A net force of 200 newtons acts on a 100 kilogram boulder, and the force of the same magnitude acts on 130 gram pebble. How does the rate of change of the boulder's velocity compare to the rate of change of the pebble's velocity? Now remember, the rate of change of velocity is actually the acceleration. So acceleration is equal to delta V delta t. And we all know that acceleration is related to the force. F net here equal to ma. So the acceleration of the boulder is less than that of the pebble for the same applied force because the boulder is much more massive. So the answer to this question, it's less than. Example. Two boxes, one heavier than the other, are initially at rest on a horizontal frictionless surface. The same constant force F acts on each one for exactly 1 second. Which box has more momentum after the fall? Let's see. F net here equal to delta P over delta T, or in other words, delta P equal to F net delta T. Now the only force acts on the boxes is F. So we have here F, and delta T, it's 1 second. So same force, same time. In this case here, delta P will be the same for both boxes. So to answer this one here, the change in momentum will be the same for both boxes. Both will have the same change in momentum. Now, in the same example, which box has a larger velocity after the force acts? Logically, the one with larger velocity is the one with the lighter mass. So the lighter one, or the one with less mass will have larger velocity. Another conceptual example. A bowling ball and a ping pong ball are rolling toward you with the same momentum. If you exert the same force to stop each one, which takes a larger time to bring to rest? Now, since both balls have the same momentum and you exert the same force, in this case here, F average equal to delta P over delta T. Now, in this case here, delta P equal to F net or average delta T. Now, same momentum and same force, which means both will take the same amount of time to stop them. Both will take the same amount of time to stop them. In the same example here, which one will have stopping distance greater than the other one? Now, to answer this question, let's back to work energy theorem. Work total equal to delta K. Now remember, the ball with less mass will have greater speed and therefore greater kinetic energy, because the relation between kinetic energy and speed is kinetic energy is related with V square. So remember here, K is related with V square. So greater speed means greater kinetic energy in this case here. And remember, work equal to F dot D. And in this case, the force is the same and the kinetic energy, which in other words, the work is more, which means the distance required to stop the less massive ball must be bigger. In other words, less massive ball will require more distance to stop. Now let's continue here. The net force acting on a single particle is described as F net here equal to dP by dt. Now, if the net force is 0, this means delta P equal to 0. In other words, P2 equal to P1, and more generally, P final equal to P initial. So the linear momentum of the particle is conserved. And this is very important conclusion. Or if we have a system of two particles, P1 initial plus P2 initial equal to P1 final plus P2 final. In other words, M1 V1 initial plus M2 V2 initial equal to M1 V1 final plus M2 V2 final. Example: a 60-kilogram archer standing on frictionless ice shoots 200 grams arrow at speed 100 meters per second to the right. What is the velocity of the archer after the shot? Now we look for here the velocity of the archer after he shoots an arrow. Now let's just have quick sketch. Here's the archer and here's the arrow. The archer standing on frictionless ice. The arrow fired with 100 meters per second. Now what is the velocity of the archer after the shoot? Now momentum is conserved, which means P final equal to P initial. MR VR initial arrow plus M archer V archer initial equal to M arrow V arrow final plus M archer V archer final. And remember, before the archer shoots the arrow, both the archer and the arrow are at rest, which means this one here 0 and this one here it's equal to 0. Now 0 equal to mass for the arrow, it's 200 kilogram or 0.2 kilogram. Now the velocity for the arrow, the final velocity of the arrow, it's equal to 100 plus the mass for the archer, it's equal to 60 times the V archer final. You rearrange this one here, you will find that V archer final equal to 20 over 60 or equal to 2 over 6 or 1 over 3 meter per second. Now another example. A 3-kilogram rifle fires 5 grams bullet with a speed of 300 meters per second. Find the recoil speed of the rifle. And remember, we compare momentum with momentum. We're not comparing mass with mass or velocity with velocity. We compare momentum with momentum. So momentum is conserved. So P final equal to P initial, or in other words, M rifle V rifle initial plus M bullet V bullet initial equal to M rifle V rifle final plus M bullet V bullet final. And again, both the bullet and the rifle both initially at rest. So this one 0 and this one here it's equal to 0. In other words, 0.005 times 300 plus 3 times V rifle final equal to 0. You arrange this one here, you will find V rifle final equal to minus 0.5 meter per second, or the magnitude of the rifle here equal to 5 meter per second. And by the way, in the previous example here, this has to be minus. It means in the other direction of the arrow. Now let's identify the impulse. Impulse. Now, if there is a net force acting on the particle, in this case, P final is not equal to P initial. If there is net force acting on a particle, then P final is not equal to P initial. In other words, F net equal to delta P over delta T, and in this case delta P equal to F net delta T, and delta P in this case here is impulse. So impulse equal to P final minus P initial and equal to F net delta T. Impulse equal to delta P, which equal to sum of all forces. By the way, F net is the same as sum of all forces here, delta T. And remember, there is impulse if there is a net force acting on a particle. But if the net force acting on a particle is equal to 0, then momentum is conserved and P final equal to P initial. Example: a 1500 kilogram car collides with a wall. The initial and final velocities of the car is 15 meters per second and 2.6 meters per second respectively. If the collision lasts 0.15 seconds, find the impulse caused by the collision and the average force exerted on the automobile. Now we have here a car moving this way here with initial velocity minus 15 meters per second. Now after the collision, the car will move this way here with velocity equal to 2.6 meters per second. So this is before and this is after. Now the impulse here equal to change in momentum, or equal to P final minus P initial, and in this case here equal to 1500, which is the mass of the car, times 2.6 meters per second minus, now 1500 times minus 15. In other words, it's equal to 26,400 kilogram meter per second. Now to find the net force acting on the car here, so impulse actually it's equal to F net, or sum of all forces, divided by delta T. Delta T here is the contact time, so F net here equal to 26,400 times 0.15 seconds. So F net here equal to 3,960 newtons. Example: a 3 kilogram ball strikes a wall at speed of 10 meters per second at an angle 60 degrees with the plane of the wall. It bounces off the wall with the same speed and angle. if the ball is in contact with the wall for 0.2 seconds, what is the average force exerted by the wall on the ball? Now let's draw the situation here. Here's the wall, and the ball, this one here, strikes the wall with equal to 60, with angle equal to 60 degree, and this is the initial, bounces back, same angle, theta equal to 60 degree, and this is the V final. Now if the ball here, in contact with the wall for 0.2 seconds, what is the average force exerted by the wall on the ball? Now F net equal to delta P over delta T, and delta P equal to P final minus P initial, which equal to M V final minus M V initial. Now since momentum is a vector quantity, V final in this case could be equal to V final, this one here, sine theta I hat with minus sine plus V final cosine theta j hat, and V initial equal to V initial sine theta here I hat plus V initial cosine theta j hat. V final is the same magnitude as the initial, which equal to 10 meters per second, and the contact time here equal to 0.2 seconds. The mass equal to 3 kilograms, theta equal to 60. Pull everything together, you will get here F net equal to minus 260 I hat newtons. Now let's discuss collisions. In one dimension. Collisions in general, two types: elastic collisions, inelastic collisions. Now let's start with elastic collisions. Elastic collisions. Kinetic energy is conserved. K final equal to K initial. So in elastic collisions, the kinetic energy is conserved before and after the collisions, and momentum is conserved, P final equal to P initial. For inelastic collisions, kinetic energy is not conserved and momentum is conserved. From this we can say that momentum is always conserved in all types of collisions, elastic or inelastic collisions, but kinetic energy is not conserved in case of inelastic collisions, and it's conserved in case of elastic collisions. Note If the objects sticks together after the collision is called perfectly inelastic collision. It's very important note here. Now let's have this model here. Two cars, as we can see here. The kinetic energy for this car here, it's equal to 0.02 joule, and the kinetic energy is the same as the first one, it's 0.02 joule. So the same kinetic energy for both cars. Momentum for this car here, it's equal to 0.2 kilogram meter per second, and momentum, it's minus 0.2 because it's a vector quantity. Now let's see here. As we can see here, the velocity it's constant for this the first card here, and the velocity for the second card here, and kinetic energy is the same for both cards. It's not changing at all. So this is before the collision. Now after the collision here, let's just stop it. The kinetic energy remains the same for both cards, and the momentum, actually the magnitude for the momentum remains the same, but the direction is switched the other way. So this one take the minus sign, and this one take the plus sign. The bounces back, in this case here, no energy lost whatsoever. So this kind of collision is called completely elastic collision. The only changes that we have here is the momentum direction. Sometimes it's this one positive, sometimes it's negative, and vice versa for the other one. Now in this model here, we have two balls, this one here and this one here, with different masses. So the mass for this one here, it's 3 kilograms, and the mass for this one here is 2 kilograms. The velocity for this one here, it's 1 meter per second, and the velocity for this one here, it's minus 0.5 meter per second. Look at what's going to happen here. After the collision, both balls will move with the same direction of the one with the larger momentum. Now, on the other hand, if we modify the velocity here to minus 1 and the mass equal to 2, while the mass for this one here it's equal to 3 and the velocity it's equal to 0.5. Look, the momentum for this one here it's minus 2, and the momentum for this one here it's 1.5. So it's expected that after the collision, both balls will move with the one with the larger momentum, which in this case, this one here. Let's see. Now the orange one drag this one to this direction. Example. A system of particles is known to have total kinetic energy of 0. What can you say about the total momentum of the system? Remember here, kinetic energy is related with the velocity. Kinetic energy here, it's equal to half mv square. Now, since the kinetic energy is equal to 0, this means v equal to 0, or in other words, all particles are at rest. So this means here, particles are at rest. Now momentum equal to mv, and v in this case it's equal to 0, so the total momentum for all the system is 0 as well. So p here equal to 0. Example. It's the opposite of the previous example here. What if the total momentum is 0? Does it necessarily that the kinetic energy of the system is also 0? Remember, the momentum is a vector quantity. So when you add up vector quantities, yes, sometimes the momentum in this case equal to 0, but that doesn't mean particles are at rest. They just cancel out when you add them together because they are vector quantities. Now in this case here, the kinetic energy is not necessarily to be 0 because the particles are moving. So to answer this question, no, it's not necessarily for the kinetic energy to be 0 in this case. Example. Now, two objects are known to have the same momentum. Do these two objects necessarily have the same kinetic energy? Now let's see. If an object with mass m and speed v, so its momentum in this case here equal to mv. Now, if another object with mass half m and 2v, in this case momentum equal to v. Now let's calculate the kinetic energy for this case here. So the kinetic energy, it's equal to half, in this case here, v square. Now let's see, the kinetic energy in this case here equal to half over 2v square. In other words, 1 over 4, this one here, 4v square. So the kinetic energy for this one here equal to v square, or the kinetic energy equal to 2 times half v square, or this one here. So the simple answer for this question is no. Now let's write down the elastic collision equations for two particles in one dimension. So momentum before equal to momentum after, or in other words here, m1 v1 initial plus m2 v2 initial equal to m1 v1 final plus m2 v2 final. And kinetic energy is conserved. And kinetic energy is conserved. In other words, half m1 v1 initial square plus half m2 v2 initial square equal to half m1 v1 final square plus half m2 v2 final square. We can simplify these two equations and write them in an easy form. So v1 final equal to m1 minus m2 m1 plus m2 v1 initial plus 2m2 m1 plus m2 v2 initial, and v2 final here it's equal to 2m1 plus m2 v1 initial plus m2 m1 m2 v2 initial. In other words, this equation here and this one here is the solution for these two equations. And remember, positive v, it means the object is moving to the right, and negative v, it means the object is moving to the left. So v is positive, going to the right, v negative, going to left. Example, consider two elastic collisions. A golf ball with speed v hits stationary bowling ball head on. The other case, a bowling ball with speed v hits a stationary golf ball head on. In which case does the golf ball have a greater speed after the collision? Now let's see this model here. In this model here, we can see, as we can see here, two cars, big one here and small one. The mass for this one is 10 kilograms, and the mass for this one, it's 1 kilogram. Now the velocity for this one is 0, and the velocity for this one is 3. So let's see what's going to happen here. Look at the velocity here, right here. It's almost 3 meters per second, or 2.5 meters per second. Now the velocity for the small car, it's the double. So if this is v for the large truck, this will be 2v. Now let's consider the other case. Now the velocity for the small car is 3. It's minus 3 because directed this way here. And the velocity for the large one is 0. Now after the collision, let's see here, the velocity for this one here is almost 0. This one almost 0, and the velocity here is the same as the velocity, it just bounces back. So the velocity here for this small car v before the collision, it's almost the same as v after the collision. Let's back to the example. Now to answer this one here, remember the relative velocity has to be equal before and after the collision. In the first case where the golf ball with speed v hits a stationary bowling ball, so the small ball here hits a large one here, heads on. So the bowling ball is almost remains stationary with velocity equal to 0, and the golf ball will bounces with the same velocity as the before the collision. In the first case here, v before the collision, the magnitude collision equal to v after the collision. But in the second case, where a bowling ball with speed v hits a stationary golf, in this case here, the bowling ball, the large one here, will remain moving with the same velocity, almost the same velocity v, and the stationary golf ball will bounces back with double the velocity, so it's equal to 2v after the collision. Now let's have an example. A 3 kilogram object traveling at 20 meters per second west collides with 5 kilogram mass object traveling at 12 meters per second again in the west. The collision is perfectly elastic collision. What is the velocity of the 3 kilogram object after the collision? So let's have here object A and object B. Now object A is moving to the west here with velocity 20 meters per second. It has to be negative here. And object B is moving to the west with 12 meters per second. Again, it's negative. the mass for this one here, it's equal to 3 kilogram, and the mass for this one here is 5 kilograms. Now, since the collision is perfectly elastic collision, the final velocity for the first object, this one here, it's equal to m1 minus m2 divided by m1 plus m2 v1 initial plus 2m2 divided by m1 plus m2 v2 initial. This one here, this one here. So you do the math, you will find the v1 final, which in this case this one here, the final velocity for the object with the mass 3 kilogram equal to minus 10 meter per second. One more example. Two particles of masses m1 and m2 moving with initial velocities v1 initial and v2 initial. If the two objects stick together after the collision and move as one object, find the final velocity of the two objects after the collision in terms of their initial velocities. Now remember, since the two objects stick together here, this collision is completely inelastic collision. In this case, only momentum is conserved. Kinetic energy is not conserved at all. So in this case, P final equal to P initial. So the momentum before the collision equal to the momentum after the collision. Now let's have here m1 and here m2, velocity it's v1 initial, v2 initial, this one here, and this one v1 initial, directed this way. Now this is before the collision. Now after the collision, now the situation is, this is the first one, this is the second one here, and both move with common final velocity. The total mass for this whole system here, it's m1 plus m2. Now only momentum is conserved, which means P final equal to P initial, or m1 v1 initial plus m2 v2 initial equal to m1 plus m2 v final. No need to name it final 2 or final 1, just v final. In this case here, v final equal to m1 v1 initial, m2 v2 initial over m1 plus m2. Example: a small car and a large truck collide head-on and stick together. Which one has larger momentum change? Now remember, momentum is conserved, and since they are sticking together here, this collision is completely inelastic collision. So P final here equal to P initial. Now the change in momentum after the collision, delta P, equal to 0 for the car and the truck combined together. Car and the truck combined. In this case here, change in momentum for the car equal to minus the change of momentum of the truck. So to answer this, they both have the same momentum change. Both example: A box slides with initial velocity 10 meters per second on frictionless surface and collides inelastically with an identical box. The boxes stick together after the collision. What is the final velocity of the system? Now, to answer this, momentum is conserved. Only momentum is conserved. Initial. Now, the first box with initial velocity here, m times 10 plus the momentum for the other box is 0 equal to, since they are stuck together or the collision is completely inelastic, in this case here 2m multiplied by v final. In this case here, v final equal to 10m divided by 2m, or in other words, it's equal to 5 meters per second. Example: on a frictionless surface, a sliding box collides and sticks to a second identical box initially at rest. What is the final kinetic energy of the system in terms of the initial kinetic energy? Now, this collision is completely an elastic collision, so momentum is conserved, or m1 v1 initial plus m2 v2 initial equal to m1 plus m2 v final. In this case here, the other box is initially at rest and the boxes are identical, which means m v1 initial equal to 2m v final, or mass with mass cancel out, v final equal to half v1 initial. Now use this one here to calculate the kinetic energy. So the initial kinetic energy equal to half m v1 initial square. Now the final kinetic energy, it's equal to half total m v final square. And remember, m here, it's equal to m plus m, which equal to 2m. Now final kinetic energy equal to half 2m, and v final here, it's equal to half v1 initial, so half v1 initial square. So rearrange this one here, you will get the final kinetic energy is actually equal to 1/2 half m v1 initial square, or it's equal to half the initial kinetic energy. Example: Sarah, 150 pounds, and Mary, 50 pounds, are standing on slippery ice and push off each other. If Sarah slides at 6 meters per second, what speed does Mary have? Now, momentum is conserved again, P final equal to P initial. In this case here, the P initial equal to 0 for both girls because they are initially standing. Now, the final momentum here, it's equal to mass for Sarah, V for Sarah, plus mass for Mary, V for Mary. Or in other words, the momentum of Sarah has to be the same as the momentum of Mary. But remember, we are not comparing mass with mass and velocity with velocity. We are comparing momentum with momentum. So the momentum for Sarah should be the same as momentum for Mary. But the mass of Sarah is 3 times the mass of Mary. So in this case here, keep the momentum is constant for both girls here. The velocity of Mary has to be 3 times more compared to the velocity of Sarah. So in numbers, the velocity here for Mary has to be 3 times the velocity of Sarah, or 18 meter per second. Example: a cannon sits on a stationary railroad flat car with a total mass of 1,000 kilograms. When a 10-kilogram cannonball is fired to the left at speed of 50 meters per second, what is the recoil speed of the flat car? So we have here a cannon, this one here, sits on railroad flat car. So if this cannon here fired a 10-kilogram ball, it's 10 kilogram, with speed 50 meters per second, what is the recoil speed of the flat car? Now momentum is conserved, and the initial momentum here, it's equal to 0, so the final momentum equal to 0 as well. Now in this case here, M for the cannon, V for the cannon final, plus M for the railroad, V for the railroad final, equal to 0. In other words, the momentum for the cannon has to be the same as the momentum for the railroad. Now let's calculate the momentum for the cannon. So momentum for the cannon equal to the mass for the cannonball is 10 times the velocity here, or it's 50 meters per second. So in total here, it's equal to 500 kilogram meter per second. Now momentum for the railroad equal to the mass for the railroad times the velocity here for the railroad, which equal to 500. You substitute numbers here, you will find V for the railroad equal to 500 divided by the mass of the railroad, which equal to, in this case, 500 divided by 1,000, or half meter per second, and it has to be to the right. Example: when a bullet is fired from a gun, the bullet and the gun have equal and opposite momentum. So if this statement is true, then why is the bullet is deadly? So to answer this one here, just remember that the kinetic energy of the bullet is much larger than the kinetic energy of the gun. A bullet having initial velocity Vb hits a ballistic pendulum of mass mb and lodges in it, stick inside it. Then the pendulum with the bullet swings up from the equilibrium position and rises up to a height h. Calculate the initial velocity of the bullet. So here's the situation. So we have here pendulum, and here's the bullet, this one here. So after the collision, when the bullet sticks inside this wood pendulum here, it rises to this new situation here, and remember this, and the bullet inside it, and here's H. We need to calculate the initial velocity of the bullet. Now to do this one here, this problem can be divided into two main problems. The first one is collisions. Actually, it's completely inelastic collisions, and the second one is a simple pendulum. So when the bullet here hits the piece of wood here and stick inside it, it rises up until the height h. So let's calculate the energy here. The energy here, since it's maximum height here, it's just potential energy. So mgh here equal to half mv initial square. Now v initial square is the final velocity for the collision case. So the v initial here is the velocity for the wood and the bullet inside it. So in this case here, mass with mass, and v actually equal to square root of 2gh. Let's just keep this one here. Now the second problem is actually completely inelastic collision. Momentum is conserved. So momentum before, it's equal to momentum after. The only momentum we have here is the momentum from the bullet itself. So in this case here, bullet v bullet initial, this is the initial momentum, it's equal to bullet plus wood, it's one piece of wood here, v final, and we just add these two masses together because the bullet sticks inside the piece of wood in this case here. The final here is actually the initial velocity we just obtained from the simple pendulum case, and this, you just simplify this one here. Now vb initial equal to bullet wood divided by bullet v final. Now let's move on to collisions in 2 dimension. Now collisions in 2 dimension, momentum is conserved in both direction, in each direction, momentum in x and momentum on y. So in this case here, instead of one equation obtained from momentum, conservation of momentum, we will obtain two equations from conservation of linear momentum, one from the px and the other one from py. Or in other words, m1 v1x initial plus m2 v2x initial equal to m1 v1x final, m2 v2x final, and this is the first one. Now the second one, the momentum along the y-axis is conserved, so m1 v1y initial plus m2 v2y initial equal to m1 v1y final plus m2 v2y final. And one equation is the conservation of kinetic energy. Now let's see this model here. The kinetic energy for this object here, it's 0.085 joule. Now the momentum is on x equal to 0.17 kilogram meter per second, and there's no momentum on y whatsoever. Now, the other ball here has kinetic energy, it's equal to 0, and no momentum on x, no momentum on y whatsoever. Now, after the collision, let's see what's going to happen here. Now, the kinetic energy for the first ball, this one here, let's name it A, and this is B. For this ball here, it's 0.025. Now, the kinetic energy for ball B, it's 0.6. So when you add up this one with this one here, you will find the final kinetic energy here equal to 0.085 joule, which exactly equal to the initial kinetic energy before the collision. Now, the momentum in this case here, each ball will have two momentums, one on x and one on y. So the one on x after the collision, it's equal to 0.05, and the one on x after the collision, 0.12 kilogram meter per second, and the one on y, 0.077 kilogram meter per second, and the one on y here equal to 0.077 kilogram meter per second. Momentum on y before the collision equal to 0. Momentum on y initial equal to 0, which means the only momentum we have here, it's after the collision. So both balls should have the same momentum. Py final for the first one plus Py final for the second one equal to 0, which exactly matches what we just got in this one here, 0.077 minus 0.077 kilogram meter per second. Now, to work with this one here, let's see, just this one moves this way here, and this one moves this way here. So this is theta, and this is beta. To find the momentum in this case, we have to analyze the x component, the y component for each ball in this one here. Example, a 15 kilogram object traveling east with a speed of 25 meter per second collides at an intersection with 25 kilogram object traveling north at a speed of 20 meter per second. The two objects stick together after collision and move in a direction that makes an angle theta with the positive x-axis. Find the direction and magnitude of the velocity of the two objects after the collision. Now, since both objects stick together, in this case here, this collision is completely inelastic collision. In this case here, momentum only is conserved, but this is two-dimensional system. In this case, momentum on x is conserved, and in this case here, on x we only have m1 v1 initial, and on x here, on the other side here, after the collision, we have the x component of v final. So m1 plus m2 v final cosine theta. Remember, the one with the angle takes the cosine. Okay, so this is the first one here. Now, on y, momentum is also conserved. So initial y equal to p final y. So m2 V2 initial equal to M1 plus M2 V final sine theta. This is equation number 2. You divide both equations. Here you will get M2 V2 initial M1 V1 initial equal to mass with mass cancel out, V final cancel out with V final here, so sine theta over cosine theta, or in other words tan theta equal to, in this case here, M2 is 25 kilograms with V2 20 divided by M1, it's 15 multiplied by 25 meter per second here, or theta equal to tan inverse 20 divided by 15, so theta here equal to 53.1 degree. Just substitute theta in one of these two equations, this one or this one here, you will get V final equal to 15.6 meter per second. Now let's identify the center of mass. Consider that we have a system of 3 masses, like in this one here. So this is mass 1, mass 2, and mass 3. Now this one here, now this one R1, R2, R3. Now the position vector for the center of mass is identified as R center of mass equal to M1 R1 plus M2 R2 plus M3 R3 divided by the total mass M1 plus M2 plus M3. Or in general, our center of mass equal to 1 over M, the total mass, summation Mi Ri, this case here, where M here equal to sum of all masses on the system. Now the components of this center of mass vector is x center of mass equal to 1 over M summation Mi xi, and y center of mass equal to 1 over M summation Mi yi, and z center of mass equal to 1 over M summation Mi zi. Now in this situation here we have three different masses. So this one here, the mass here for this one it's 0.17, and the mass for this one here it's 0.057 kilogram, and the mass for this one here it's 0.16 kilogram. Now we look for, or we need to calculate the center of mass. So x center of mass in this case here equal to M1, so the mass M1 here 0.16 times the position, the x position for this one here, it's minus 0.19 plus M2 0.17 times the position here, the x position equal to 0 plus 0.057, this one here, and the position of x for this one, it's 0.3, divided by this one here, m1 0.16 plus 0.17 plus 0.057. You do the math, you will find the x center of mass position. Now y center of mass, in this case here, again it's 0.16 times the y position is 0.12 meter, plus for the second one, this one here, the 0.17 times the y position, it's 0.4, plus for this one here, it's 0.057, this one here, times 0.25 meters, divided by the total mass, it's 0.16 plus 0.17 plus 0.057. And this is the position of y, or y center of mass position. Example: two equal mass particles A and B are located at some distance from each other. Now particle A is held stationary while particle B is moved away at speed v. What happens to the center of mass of the two particle systems? Now let's assume that particle A is located at the origin. So x here equal to 0, particle A, and particle B located a distance x from A. Since they are equal, the center of mass in this case here, it's equal to x over 2. So this is the center of mass, x center of mass in this case here. Now, if V equal to delta x over delta t, now the position of B is changing, which means the center of mass is changing as well. In this case, V equal to delta x over 2, this one here, over delta t, or simply it's equal to half V. Example: a system consists of three particles located as shown. Find the center of mass of the system. The masses of the particles are m1 equal to m2, which equal to 1 kilogram, and m3 equal to 2 kilograms. Now in this case here, m1 here located at position 1 on the x, and m2 located at position 2 on the x, and m3 located at position 2 on the y. Now x center of mass in this case here, it's equal to m1 and its position x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. Now m1 here, it's equal to 1 times the distance from the origin here, it's just 1, plus m2, again it's 1, and the distance is 2, plus m3, this one here, and the distance is 0, here 0, divided by 1 plus 1 plus 2, 4. So the center of mass, x center of mass in this case here, equal to 1 plus 2, 3 over 4 meters. Now y center of mass equal to m1 y1 plus m2 y2 plus m3 y3 divided by total mass m1 plus m2 plus m3. Now y center of mass, there is no y position for m1, not even for m2. Now it's equal to 2 times its position 2 divided by the total mass, it's 4, and it's equal to 4 divided by 4, it's equal to 1 meters. R center of mass in this case here, it's equal to X center of mass I hat plus Y center of mass J hat, or 0.75 I plus 1 J hat in meters. In the graph here, now X equal to 0.75, it's somewhere, just change the color here, it's somewhere here, and this one here, so it's almost somewhere here. This one is the center of mass. That's it. Thank you for watching.